Let's look at two definitions for acids and bases, Bronsted-Lowry and Lewis. And we'll start with Bronsted-Lowry. So a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. Let's really quickly review what a proton refers to. So for a neutral hydrogen atom, the most common isotope has one proton in the nucleus. So here's my nucleus, here's my one proton, and one electron outside of the nucleus. So here's my electron. If we take away the electron, we're left with just that proton. We're left with the nucleus of a hydrogen atom. So we could also say this is equal to H+. So when you're talking about a proton donor, that's something that's donating an H+, and a proton acceptor is accepting that H+. Let's go down here to the dot structure for HCl. Let's focus in on that covalent bond. All right, one of those electrons came from the chlorine, so let me go ahead and draw on that electron here. So one of the electrons in the bond came from the chlorine, and one of the electrons in the bond came from the hydrogen, so in magenta right here. So that electron, that's talking about this electron right here. HCl is going to donate a proton to water. So let's go ahead and show what happens. A lone pair of electrons on the oxygen is going to pick up this proton right here, and the electron in magenta is left behind. So these two electrons come off onto the chlorine. So let's go ahead and draw the products. So we would have, we had an oxygen bonded to two hydrogens, but the oxygen just picked up a proton, so now it's bonded to 3, which gives the oxygen a +1 formal charge. Let's show those electrons, right? So these two electrons in here in red are going to pick up this proton, and those two electrons in red are going to form this bond right here. So this is H3O+, or hydronium, the hydronium ion. All right, the chlorine, right, it becomes the chloride anions. Let's go ahead and draw that in. So we had 3 lone pairs of electrons, and we got one more lone pair, right? So the electron in green is on the chlorine, and so is the electron in magenta. So the chlorine picked up a negative charge. It becomes an anion. So we get the chloride anion here. So the HCl donated a proton. So it's a proton donor. It's a Bronsted-Lowry acid. So let me go ahead and write that here. So Bronsted-Lowry acid. And water accepted the proton. It accepted an H+. So water is the Bronsted-Lowry base. All right, let's think about the possibility of the reverse reaction. So if you think about what must happen, the chloride anion must function as a base and pick up a proton from the hydronium ion here. So if you think about the reverse reaction, I'll put a really tiny arrow going back in reverse because the equilibrium lies far to the right. But if you think about it in reverse, the chloride anion would function as a base. And this is actually the conjugate base to HCl. So let me go ahead and write that here. So conjugate base to HCl. So we have a conjugate acid-base pair here. So let me go ahead and write that over here. So we have HCl and Cl-. And think about the difference between these two, right? There's one H+ difference between that conjugate acid-base pair. All right, so over here, water function as a base. Once it picks up a proton over here, it could function as an acid. So this would be the conjugate acid. So let me go ahead and write that. This is the conjugate acid to our base over here, to water. So we have another conjugate acid-base pair. So let me go ahead and write that over here. So we have H2O, and H3O+ is another conjugate acid-base pair. And once again, think about the difference between these two, right? Between H2O and H3O+, there's one proton difference, one H+ difference. And so when you're dealing with the Bronsted-Lowry definitions for acids and bases, think about one proton. All right, let's move on to the Lewis definition. So let's get some room down here. So the Lewis definition, a Lewis acid is an electron pair acceptor. And a good way to remember that is we have an A here for acid and then electron pair acceptor, so an A right here. And a Lewis base is an electron pair donor. And a good way to remember this is if you have Lewis base, right? So like a lowercase b for base, right? Over here, electron pair donor. If you take this b here and just flip it, right, then you would get a d. So that's a nice way to remember that a Lewis base is an electron pair donor. All right, let's look at the dot structure here for boron trifluoride. Notice that boron does not have an octet. All right, so if we count the number of electrons, here's 2, 4, 6 electrons around it. So it's not an octet. This boron right here, let me go ahead and draw this in. This boron is sp2 hybridized, right? If it's sp2 hybridized, it has an empty p orbital. So we have an empty orbital, which I'm going to represent like this, and that empty orbital is capable of accepting a pair of electrons. So boron trifluoride is going to function as a Lewis acid here. And water has a lone pair of electrons that it can donate. So water is going to function as a Lewis base. So a lone pair of electrons on the oxygen, right, we're going to donate that lone pair right into the empty orbital here. We're going to form a bond between the oxygen and the boron. So let's go ahead and do that. So the oxygen was bonded to 2 hydrogens already. We're going to form a bond between the oxygen and the boron. And this oxygen still has 1 lone pair of electrons left, which is going to give this oxygen here a +1 formal charge. And the boron is bonded to 3 fluorines. And I'm just not going to draw on the lone pairs of electrons around fluorine to save some time here. This gives the boron a -1 formal charge. So let's show those electrons. So let me go ahead and highlight this electron pair in red here. So this pair of electrons gets donated, right, to boron to form this bond right here. So notice there's no H plus changing here, and so that's why the Bronsted-Lowry definition doesn't apply to this acid-base reaction. We have to use the Lewis definition. And so the Lewis definition is a little bit more broad, actually, and we can go back up here to the previous reaction, right? And we can look at the definition for Lewis acid and base for this one. So a Lewis base is an electron pair donor, and notice that's what water is doing here as well. It's donating a pair of electrons. So not only can we say this is a Bronsted-Lowry base, we could also say this is a Lewis base. And what's accepting that pair of electrons? Right? Well, it's the protons. Let me go ahead and draw this out. Right? So HCl, you can think about HCl as being H plus and Cl minus. And that lone pair of electrons, right? This pair of electrons is being accepted by the proton. So you could say that this proton here is a Lewis acid. Let me go ahead and use a different color for that. So we could say that this proton here is a Lewis acid. It's accepting a pair of electrons. So you could say that HCl is a source of a Lewis acid, which is H+. All right, so these are very important definitions to understand.